Welcome to our session on the LongLora fine-tuning strategy, part of our interview prep series. Today, we'll explore the intricacies of fine-tuning models for long context scenarios. We'll start by discussing the motivation behind this approach, then delve into how sparse attention mechanisms enhance efficiency. Finally, we'll examine distributed solutions that make this strategy scalable. Stay tuned as we unpack these concepts to help you master long context fine-tuning. Welcome to the Interviewer's Mindset slide. Here, we delve into how technical questions are designed to evaluate your understanding of LongLora. Interviewers assess three key dimensions. First, awareness. Have you familiarized yourself with the paper and its core concepts? Second, motivation. Can you articulate the problems LongLora addresses and its context? Lastly, mechanism. Are you able to clearly explain the technical solutions it provides? Understanding these aspects is crucial for effective communication. Today, we're diving into the rapidly evolving landscape of large language models. These models are racing to expand their context windows, with GPT-4 Turbo now supporting up to 128,000 tokens and Kimi reaching 200,000. However, this expansion isn't without challenges. The key bottleneck lies in self-attention memory and compute, which scale quadratically with sequence length. This means doubling the context results in 4 times the computational cost, making straightforward fine-tuning highly expensive. In this slide, we're exploring the quadratic complexity of standard self-attention mechanisms. Essentially, these mechanisms calculate relationships between every pair of tokens, which leads to memory and compute requirements that scale as OS can natter with the sequence length. This becomes particularly challenging at scales of 128,000 tokens or more. Our goal here is to reduce this complexity to a sub-quadratic level, ensuring efficiency without compromising the quality of the model's performance. Welcome to LongLora's core insight. During fine-tuning, we use shifted sparse attention, or S-squared add-in. This approach is local, grouped, and low cost, allowing us to efficiently fine-tune the model. However, when we move to the inference phase, we switch back to standard global attention. This ensures full quality without approximation. The key here is asymmetry. We minimize costs during training while maintaining high model quality during inference. On this slide, we explore S model squared, attention, specifically focusing on the second scoring point, shifted sparse attention. This involves global attention and a shift half-group approach within local groups. The shift operation plays a crucial role by enabling neighboring groups to exchange information. This exchange helps prevent information silos, ensuring that the model remains stable and effective, even when processing long documents. This innovative attention mechanism is key to enhancing model performance. Welcome to the key properties of SES-Convash state, a picturist. First, we have local grouping, where input is split into smaller groups, allowing attention to be calculated within each group and significantly reducing the attention matrix size. Next, the half-group shift ensures tokens near group boundaries can still interact with neighboring groups. Finally, by integrating LoRa, we achieve parameter-efficient fine-tuning, extending context length with minimal computational cost through LongLora. Let's explore some common sparse attention mechanisms. These methods aim to reduce computational complexity by focusing on the most relevant information. One popular approach is the fixed pattern method, which uses predefined sparsity patterns. Another is the learnable pattern method, which dynamically adjusts to input data. Lastly, there's the local attention method, which restricts attention to nearby elements, improving efficiency for large-scale tasks. Let's delve into Atrous self-attention. This concept is inspired by dilated convolutions, where attention is calculated in a strided pattern influenced by a dilation parameter, k. By allowing each token to focus on only n divided by k elements, we significantly reduce memory and computational demands. This approach brings down complexity to just 1 over k of the original. However, it's important to note that this might lead to missing some dense local context. In this slide, we explore the concept of local self-attention. The core idea here is that each token focuses only on its immediate neighbors within a window of size k, ignoring anything beyond that. This is similar to how a standard convolution works with a 2k plus 1 window. However, the key difference is that while convolution uses a fully connected layer, local attention relies on a weighted average, facilitated by the softmax mechanism. Today we're exploring OpenAI's Sparse Self-Attention, which smartly combines Atrous and local attention. By alternating between these, we achieve both local density and global reach. Local attention ensures dense connections within a k distance, capturing nearby context effectively. Meanwhile, Atrous attention creates sparse connections at multiples of k, efficiently reaching remote contexts. This leads to an attention matrix that's zeroed out except within k and at multiples of k, optimizing correlations and reducing memory usage. Welcome to this slide on sparse attention for long texts with BigBird. Traditional transformers struggle with long sequences due to their quadratic complexity. BigBird innovates by using a combination of 3 distinct attention types, which significantly reduces this complexity from O-denomomen squared to O-denomomen. This allows BigBird to efficiently handle much longer sequences than before, making it a powerful tool for processing extensive text data. Introducing BigBird's 3-part attention design. First, global token attention allows certain tokens to access the entire sequence, maintaining global context efficiently. Next, local neighbor attention ensures each token connects with nearby tokens, capturing local structure effectively. Lastly, random token attention enables tokens to attend to select random tokens, offering global coverage with minimal overhead. BigBird also uses gradient checkpointing to extend sequence length, optimizing training time. In this section, we explore ways to enhance long context handling in AI models. First, consider redesigning position encoding, such as rope or alibi, to support longer contexts beyond the training window. Next, think about combining sparse attention with hardware-optimized kernels like flash attention to alleviate memory bottlenecks. Finally, when a single GPU's memory is maxed out, distributing attention across multiple GPUs becomes crucial. How would you tackle these challenges to push boundaries further? Welcome to our discussion on ring attention and its innovative approach to distributed long context processing. By leveraging a linear scaling of context length with the number of GPUs, ring attention represents a significant advancement in sparse attention methods within distributed systems. This allows for more efficient processing of large datasets, enhancing both speed and performance. Join us as we explore how this powerful extension can transform your computational capabilities. Welcome to ring attention, how it works. In this approach, we achieve exact full attention using a multi-GPU setup. By employing ring passing, key and value vectors circulate across GPUs, allowing each to compute attention locally. With this method, each GPU holds a fraction of the context, ensuring linear memory usage while maintaining precision. Ring attention extends blockwise optimization beyond single GPUs, enabling precise attention without approximation across the entire dataset. Today, we're tackling the 2 main bottlenecks in long context training: memory and computation. By combining sparse attention and ring attention, we achieve significant improvements. Ring attention distributes the context across multiple GPUs, ensuring memory scales linearly with the number of GPUs. Meanwhile, sparse attention reduces the computational load on each GPU, removing the quadratic cost per shard. This approach results in linear memory expansion and sub-quadratic computation, making large-scale long context tasks more efficient. Welcome to the Interview Answer Framework. To excel, structure your responses strategically. Begin by discussing the background to highlight your understanding of the problem. Next, provide a high-level overview of your solution before diving into specifics. Use diagrams or equations to elaborate, showcasing your depth of thought. Finally, anticipate follow-up questions by connecting to related methods like Big Bird or Ring Attention, demonstrating a broad grasp of the topic. In this slide, we explore LongLora's innovative approach. The core trick here is using S-squared attention, which combines sparse and shifted attention during fine-tuning and switches to global attention during inference, giving us the best of both worlds. We also delve into the evolution of sparse attention mechanisms, from Atrous to Big Bird, each enhancing context capture. Finally, by integrating ring and sparse attention, we efficiently overcome memory and compute constraints for longer context processing beyond a single GPU. Let's dive into how to nail your interview. First, make sure to hit the key scoring points and structure your answers clearly. Connect your ideas to show depth and insight. When faced with open-ended questions, seize the opportunity to shine by approaching them from multiple angles. This demonstrates your genuine problem-solving abilities. Remember, the goal is to communicate effectively and leave a memorable impression.